All right, we're very privileged to once again have our distinguished speaker, Josh Willis, JPL, NASA climate scientist. He's the man. It's been a very interesting year for climate change data and how that's been absorbed into the general media and part of the educational process. We absorb some of that. We absorb the data. We try to make sense of it. Our reason for having Josh here today is to extend that, to basically have us enabled to make the best sense out of that data that's coming out of satellites, coming out of real-world observations. Josh's specialty has been the oceans, how climate change is impacting the oceans, and how we can project into the future what we might be expecting. With the latest release of the IPCC's 5th report, there's data to be assessed, but some of that data takes us in, or can take us in directions that open up a whole lot of policy questions to us. Policy will not be the focus of what we want to talk about today. It's really addressing the science. What is the science telling us? What is it showing us? So we'll have Josh will do his presentation and leave a little bit of time towards the end for any kind of questions that might come up. And I'm sure that there may well indeed be questions already in your head, and there may be questions that are raised through the presentation. So without further ado, I would like to have a nice welcome applause for Dr. Josh Willis.
Thank you, sir.
Thank you.
Appreciate it. Hey, everybody. How you guys doing? Good, good, good. You know, whenever I'm on a college campus, it always reminds me of this professor that I had. It was a math professor, Professor Bird. And he would always say, you know, it's fun to have fun, so let's have a little fun, shall we? And then he'd do some complicated equation on the board, and he'd say, wasn't that fun? So it's fun to have fun. I think that's a good philosophy. So I'll start off. So I'm going to try out a little bit of my global warming jokes on you at the start here, and we'll see how they do. And then when you guys don't laugh, we'll continue on to the rest of the stuff, and it'll be great. What's that? Look for eye rolling. Okay, yeah. So, you know, global warming's definitely causing sea levels to rise, which means that one thing is certain, Gary Coleman is going to drown. No? You guys don't even know who Gary Coleman is anymore, do you? The wee man. He was small. It's so hot outside that my orange tree was actually producing tang the other day. Yeah? No? Oh, there was a groan. I heard a groan. Yes. It's so dry that my grapevine is growing raisins now. Actually, the North Pole has gotten so warm that this last year, air traffic control grounded Santa's sleigh for 45 minutes while the elves cleared tumbleweeds off the runway. No? Too much of a stretch? Okay. So anyway, in addition to doing global warming talks like this every once in a while, I also do stand-up comedy. I'll be here all week. Just kidding, not really. But I do stand-up. No, but not really. Anyway, but I want to give you guys a little bit of a rundown of some of the stuff that I do as a scientist, a little bit of work on climate change and sea level rise, show you some of the data that's used to say what's happening to our planet's climate and why, and try and give you a sense of really just what's going on and what role humans are playing in our global climate. And I'm actually trained as an oceanographer. I went to college in San Diego, or went to grad school in San Diego at the Scripps Institution of Oceanography. And so I tend to think of climate change kind of from the perspective of the oceans. And I always start off my talk with this picture of the Earth, which is no news to anybody who's downloaded Google Earth. You know, you can spin the Earth around and look at it from any angle. And if you just spun this globe, spun it just a little more east, yeah, a little more east, almost the only thing you would see from this angle is the Pacific Ocean. So the Pacific Ocean is 1/3 of our planet's surface area. And 2/3 or over 2/3 of the planet's surface is covered by water, is covered by the oceans. So if we're changing our global climate and driving our planet into a warmer climate, you can imagine that a lot of that change is going to be happening in the oceans. As a matter of fact, Arthur C. Clarke once famously said that we really shouldn't even call our planet Earth. We should call it ocean, because most of it's ocean, right? Only 1/3 of it is Earth. So keep that in mind as you think about climate change and as you think about global warming and stuff. Really, almost all the action is happening in the oceans, and that's where we look to see the biggest impacts so far. So people often confuse weather and climate. So whenever there's a big heat wave or whenever there's a big snowstorm, it doesn't matter. There's always some kind of weather going on when there's a big typhoon in some place like the Philippines. A huge, devastating typhoon struck the Philippines. These things are part of our natural weather that we've been getting for thousands of years. And there might be small changes in the natural order of the weather that we're getting, but really, whenever you see a big storm or a big heat wave or something huge on the news, oftentimes that's just the kind of thing, that's just the kind of natural weather cycle, natural weather event that we've been having for thousands of years. So it's important not to confuse weather and climate. Weather is something that happens very quickly. It changes all the time, and it tends to have big extremes. So you have big heat waves, you have big storms, and climate is kind of like the long-term average over those things. So just remember the next time you go see a global warming talk and there's a big snowstorm, don't assume that that means there's no global warming. Because of course there's still weather happening, there's still storms that are going to happen, but that doesn't mean that the climate isn't changing and in a really big way, and in a really big way we can see and measure. So don't postpone your global warming talk just because there was a snowstorm. Because this is weather, it's not really climate. But that doesn't mean that global warming isn't real. There's plenty of folks who will say, oh, well, we just had a big snowstorm. There can't possibly be any global warming, right? But no, that's really not true either. The weather is kind of a foil for both sides in this political battle anyway, because oftentimes people point at the weather and say, oh, look, the weather's crazy, we have global warming. Or people say, oh, look, the weather's cold, there's no global warming. But really, global warming is still happening, and we have to remember not to pay attention to the bully. We don't have to say global warming is a myth. It's really not a myth. So what is climate? If I say the climate is changing and the planet is warming, we define climate as really the long-term usual weather conditions of a big area, a region, a planet, or a country. It's also, you know, if you think about it, every year we go through winter and summer, right? We have seasons. These are part of the climate, and every year those seasons change. So climate change is kind of happening all the time, and there is natural climate cycles as well. There's climate cycles just like the seasons. There were cycles hundreds of thousands of years ago where the Earth went through warm and cold periods, and I'll talk about those a little more in a bit. But you have to remember that not only is the weather changing naturally, but the climate also has certain natural changes and natural cycles that happen as well. But what's different about what's happening now is that humans are beginning to be one of the major forces in driving our planet's climate. So when we talk about global warming, what we really mean in terms of global warming is this graph right back here. This is a graph showing the increase in the temperature of the atmosphere over the last 130 or so years. And you can see that it's gone up by 1.5 degrees, roughly. About 1.5 degrees in 100 years, Fahrenheit. So a little less than 1 degree Celsius. Now that doesn't sound like a lot, right? Because if you go outside and it's 72 today, and it's 65 tomorrow, and it's 85 the next day, those are huge changes in temperature, right? But you have to remember, this is the average temperature over the whole surface of the planet. So we're using it to kind of as a shorthand for how the planet's climate is changing. So usually when people talk about global warming, this is what they mean. They mean that slow, steady warming that's happened over 100 years, not over 5 years or 10 years, but really over 100 years. That's really undisputable. We know this is definitely happening. And we also know that this is caused by human activities. So if we look back at the climate for the last couple 10,000 years, we get this really interesting picture, because about 20,000 years ago, our planet was covered with ice. There was way more ice covering North America and a lot of northern Europe. It was an ice age, essentially, a big block of ice that reflected a lot of sun. The overall temperature of the planet was much colder, 5 degrees Celsius colder. So that's like 9 degrees Fahrenheit. And then over the next 10,000 years, between 20 and 10,000 years ago, we warmed up out of this cold period. And that happened sometimes quickly and sometimes slowly, but really on average, it was a pretty quick warming. And then we had a stable climate. For about 10,000 years, climate on the planet Earth was very stable. We had fairly warm temperatures, pretty close to what they are today. That doesn't mean there was no climate change. There was this little medieval warm period when Vikings settled Greenland, and then the little ice age when a lot of settlements in Greenland had to be abandoned because it got too cold and there was ice floating in the Thames River in London. So we've been through these climate changes in the past, but really nothing compared to coming out of an ice age into what we call the Holocene. That's what this is called. This period is called the Holocene. And that's about the last 10,000 years. So what we're looking at in the next 100 years is to warm up the planet out of this warm period by another 2 to 4 degrees Celsius. Probably in 100 years, it'll be somewhere between 2 and 4 degrees Celsius warmer than it was. So this change is getting to be comparable to the difference between a warm period and an ice age. And so an ice age was a huge, very different, very dramatic climate. And in fact, we weren't able to form civilizations until this 10,000 year period of relative climate stability. So in fact, things like farming and cities and nations and technology, iPhones, all this grew up during the period of this 10,000 years of a stable climate. So what we're looking at is the next 100 years, we're driving our climate into a totally new regime that we haven't seen and that humans haven't really experienced any time in their existence. So it's a pretty big change that we're talking about. So, okay, what causes global warming? Now that you're all nice and asleep, wake up and tell me something. What causes global warming? Burning fossil fuels, somebody said, greenhouse gases. A lot of people actually say the answer I was looking for was Democrats. Democrat, thank you. Someone's seen this talk before. No, but I like to make fun of Al Gore because he's funny. Remember, it's fun to have fun, and Al Gore's fun. Anyway, it's fun to have fun, and Al Gore basically got the answer right. Although he's a big political figure, and there's a lot of politically charged language and discussion about his movie, An Inconvenient Truth. Essentially, the movie got the basic facts of global warming right. The planet's heating up, and people are the cause. So don't blame Al. He's just the messenger. But what really causes global warming is, just like you guys said, it's carbon dioxide and people burning fossil fuels. So this graph really is one of the most stark signals that we're changing the planet that we have in the climate record. If we look back 100,000 years, several 100,000 years, we went through this period of warm period and then cold ice age, and then warm period and then cold period. And these are punctuated, like this one. We tend to come out of these cold periods rather quickly and then have a long warm period that's relatively stable. And that's essentially what had happened about 20,000 years ago. We came out, we were in a warm period, we had a very stable climate, and then this is carbon dioxide in the atmosphere over this period of time. And then in the last 150 years, we've increased the carbon dioxide level to higher than it's been any time in the last several 100,000 years. And this last year, we actually hit 400 parts per million in the atmosphere, which hasn't happened in probably several million years. So we're really changing the whole composition of the atmosphere in a way that no sort of living thing and no sort of modern species has seen. So we've been through all these big climate hills and valleys, but we haven't seen anything with this much CO2 in the atmosphere anytime in over 1 million years. And how do we know that? Well, one of the ways, and I think it's important as we go along and you look at this data and you see these graphs, is to kind of understand where they come from. And the record of carbon dioxide, as you go back in time, comes from places like this. This is a glacier in Peru. And every year, a little bit of snow falls, and then some of it melts, but it doesn't get warm enough to completely melt away. And then a little more snow falls the next year, and a little more the next year. And you can actually see the annual layers year by year. You can count back in time, and you can see how the carbon dioxide changes over time, because when the ice melts and the snow accumulates, it traps little bubbles of air. And so we actually have a record of how much carbon dioxide was in the atmosphere for hundreds of thousands of years if you drill down into these glaciers. And in fact, it's not just the composition of the atmosphere, but you can also actually tell the temperature of the atmosphere separately, because the isotopes of things that are absorbed and so forth depend very strongly on the temperature. So by kind of looking at the different isotopic ratios as you go back down through the record, you can also reconstruct the temperature of the atmosphere separately from the amount of carbon dioxide in it. And that's really how we have a lot of our very detailed knowledge of these records of climate change over the last several million years. So now I'm going to talk a little bit about how global warming works. So I've said that we're adding carbon dioxide to the atmosphere, and there's no question that it's humans that are causing that, because you can actually take the CO2 back out of the atmosphere, and you can weigh the carbon. You can look at the isotopic ratios of the carbon, and you can figure out that the carbon that's added to the atmosphere actually came from burning fossil fuels, because it has the same isotopic ratio. So it's like a little marker, it's like a little flavor of the carbon that's in the atmosphere. So we know that it's humans that are putting that extra carbon dioxide in the atmosphere. So what does that carbon dioxide do? Well, if you think about the globe in this kind of simplified way, all global warming talks have this same picture. And essentially the sun is giving us all of the important energy that drives our climate system. So we get all of our energy from the sun, and it comes in the form of visible light, just like the light that's bouncing off my face, hitting you guys in the eyes right now. This visible light goes right through the atmosphere, because the atmosphere is clear, transparent to this visible light. That visible light then warms the surface of the Earth, and then the warm surface of the Earth sends heat energy back out towards space in the form of infrared radiation. But this outgoing radiation reacts differently with the atmosphere. And when you add carbon dioxide to the atmosphere, it traps more of that outgoing heat, the heat that's trying to get back out into space. So the question is, what happens to that extra heat? Where does it go? Anybody know? Somebody said it, yes, the oceans. What happens to the heat? Over 90% of the heat that gets trapped from these greenhouse gases winds up warming the oceans. So think about that for a second. 2/3 of the planet is ocean, but 90%, like 95% of this extra heat is actually warming up the oceans. Why is that? The reason is because of a very simple property of water. Water is really heavy, and it's really hard to change water's temperature. So it has what we call a very high heat capacity. That means it can suck up a whole lot of heat. And you can demonstrate this with a really simple trick. If you take a balloon and you fill it with air and you hold a flame to it, what happens? It pops, right? But if you take a balloon filled with water and you hold a flame to it, you could actually stand there all day and the balloon won't pop. And the reason is because the water is so good at absorbing that heat that the rubber on the balloon doesn't have time to melt and it won't pop, right? I can tell you're all kind of skeptical. I think we should try this. So I brought a balloon and a lighter. I think maybe, you have such a lovely stage. I think I'm just going to get up on the stage here for a second. I didn't know there would be a whiteboard, by the way. I would have totally done this differently if, not really, if there was a whiteboard. But so if you take a balloon and you fill it with oxygen or air or whatever's coming out of my lungs, it's not smoke, I don't smoke, I promise. Think that's big enough? Yeah. Kind of lightheaded now. If I fell off the stage, run. I might injure you. Been eating a lot of heavy foods lately, kind of gaining some weight. I might really crush somebody if I fall, so please be safe and run very fast. Here we go. So our balloon filled with air, and here's my lighter. So I'm just going to hold this to the balloon, and you guys count how long it takes for the balloon to pop. Okay, you ready? You sure? All right, here we go. Wow, that was really loud. Sorry about the mess. But so that's what happens when you fill a balloon with air. But like I said, if you fill a balloon with water, then you could really stand there all day and it won't pop. And I've done this many, many times before, and the balloon never pops. It really is perfectly safe. You can try this at home. You won't get wet. You don't even need to do it over the sink because really it's like science, guys. It's safe, you know. No balloons will be harmed in this next magical trick. I swear to God, this is just a prop. It's just for me. So here's our water balloon. Oh yeah, I filled it up a little earlier. You guys ready? I'm sorry I didn't bring any bags for you guys, but I was out of bags. So here we go. Just count off how long it takes for the balloon to pop.
1, 2, 3, 4.
Boom!
7, 8, 9.
See any good movies lately, or? I missed Man of Steel. I really wanted to see that one. Just got to wait for it's out on video. Awesome. I'm going to Netflix that sucker. So, you guys learning a lot in school? So, you can actually stand there for a really long time, and if you want to feel the front of the balloon, it's not even hot, right? She said it. It's not hot, people. It's not hot. So there we go. It works. Yay! Science. So really, this is an important concept, though, right? Because remember, 2/3 of our planet is covered with that stuff, and by that I mean water balloons. So really, climate change is happening not just to the atmosphere. That graph that I showed you at the beginning, that's what's happening to the atmosphere. It's also happening to the oceans, and really most of it's happening to the oceans, right? Over 90%. So if we think back to that little diagram that I drew where we had the sun, and it's giving us all this energy in the form of visible light, then it would look something like this, right? And if our planet stayed the same temperature, then the amount of energy coming in would equal the amount of energy going out, right? So it would be balanced. We would have incoming energy in the form of the sunlight and outgoing energy in the form of this infrared radiation headed out to space, and they would be balanced. But when we change the atmosphere, we keep some of that extra heat that was going to make it back out into space. And that extra heat warms up the Earth. So our happy Earth goes to our hot Earth, right? Now, eventually, when the Earth gets to be a high enough temperature, it starts to radiate more energy back out into space, just because it's warmer, because hotter things send more energy out into space. So eventually, our Earth will make up that difference in incoming and outgoing radiation. So eventually, the outgoing radiation will grow enough to balance the incoming radiation, the incoming energy. And when that happens, we'll have sort of a new stable climate. But the penalty for that new stable climate is that we have a hotter Earth. So in the process of this, we had to heat up the Earth in order to get more energy to go back out into space and eventually reach a new balance, right? So the thing is, remember, heating up the Earth, we're really heating up the oceans, right? We have to really heat up the oceans in order to change the climate because they're sucking up 90% of this extra energy. So to heat up the oceans actually takes something like 1,000 years in order to heat the oceans from top to bottom. Now, most of climate change happens much quicker than that, in decades or 100 years, something like that. But because you don't really have to heat the whole ocean. But the ocean continues to react. Mostly, we feel what's going on at the surface of the ocean. So the ocean is going to continue to react to whatever carbon dioxide we put in the atmosphere. It'll keep reacting to that for thousands of years. In fact, sea levels will continue to rise that entire time because they're still soaking up heat and the water gets bigger when it heats up. It literally expands. So we're going to continue to see sea level rise for thousands of years after we put this carbon dioxide into the atmosphere. So that's kind of how global warming works. But let's talk about whether or not global warming is real. Some people would say that global warming is not real. You guys know this guy? No? Rush Limbaugh. You're all too young. No, this is Rush Limbaugh. He still has a radio show, but he doesn't look nearly this good anymore. But he likes to say things to suggest that global warming isn't even happening. And in fact, a few years ago, I wrote a paper and had kind of a surprising result. And Rush Limbaugh said that because it was surprising, we had no idea what we were talking about in terms of the climate. In fact, he said, to overturn the world economy based on the musings of a few idiot leftist scientists is just stupid. And that's what global warming is actually all about. So I had some business cards made up that say idiot leftist scientist on them if anybody wants one. But there are these people that are still out there today basically telling us that global warming is not happening and that people are not the cause. And while we could have a long debate about what to do about global warming, we really can't debate the fact anymore that it's happening. It's definitely happening. And here's some of the evidence that it's happening. My furry friends. This was a movie a couple years back, Ice Age 2, and I loved it because sea level rise was the villain in this movie. It's the only movie I'm aware of where sea level rise was the bad guy. These guys were running away from a warming climate and all this ice was melting. And sea level rise is something that we can measure quite clearly. It's a response of our Earth to climate change, and we can measure it very easily today. If we look back again at the last 10,000 years, so from between about 10,000 years ago and about 5,000 or 6,000 years ago, we were still warming up out of this cold period. Remember there was a big ice sheet over North America? Well, all that ice melted, and when that ice melted, it ran off into the ocean and it caused sea levels to rise. And they rose really, really fast for thousands of years. We had very fast sea level rise. And finally, 5,000 or 6,000 years ago, they leveled out. And for the last several thousand years, Earth hasn't seen any sea level rise to speak of until about 1850. And after about 1850, sea levels started to rise at about 2 millimeters per year. And we can actually measure this quite well now. There was a recent paper that I'm really excited about, it's kind of neat, that shows sea level rise along the US East Coast. And there's a place in the US East Coast where the ground is actually rising up, and we can measure that pretty accurately. And we know it's been doing that for thousands and thousands of years. And as it rises up, the tide, the water actually creeps down the beach slope, and as it does, it leaves a record of where the water was at different times. And by measuring little critters that are in the water in a very narrow range of the tidal zone, they can actually figure out, they can reconstruct the height of sea level back in time. And so this is a reconstruction of sea level along the North Carolina coast for the last 2,000 years. And what you see is that about 2,000 years ago, sea level was perfectly stable. So we had a very stable sea level. And then 1,000 years or so ago, remember we had that medieval warm period, so there was a little bit of sea level rise. And then it leveled off. We had a little ice age, and there was maybe a little bit of sea level drop, but not too much. And then the last 150 years, right here at the end of the record, you see it turns up and follows the tide gauges nearby and rises at a rate of about 2 millimeters per year, which is about the global rate we've seen for the last 100 years. So this is a really neat record. It's what we call a hockey stick diagram because it looks like a hockey stick lying on its side. It's kind of flat, and then it goes up at the end. So we finally have sort of a hockey stick for sea level rise, and this gives us a good indication that really what's going on in the last 100 or 150 years is something that hasn't happened any time in the last 2,000. So we know beyond a shadow of a doubt that this 100 years, 150 years is really special. Why is it special? Because we've increased the carbon dioxide in the atmosphere from 280 parts per million up to 400 parts per million. So we're getting close to another couple of few decades, we will have doubled the amount of carbon dioxide in the atmosphere. So we know beyond a shadow of a doubt that we're changing the climate, and that really this warming, this sea level rise, the temperature increase, the melting ice caps, the disappearance of glaciers, all of this is a direct result of the carbon dioxide that we're putting into the atmosphere. So if we look a little more closely at the sea level, we can zoom in on that last little part, the last 150 years or so. And we have pretty good records because we have tide gauges that actually go back well over 100 years in different places around the Earth. And we can reconstruct what sea level was like from actual direct instrument measurements for the last 130 years or so. And what's interesting about this, it's about an 8-inch rise globally, which doesn't sound like much when you're standing on the beach watching the 6-foot waves crash in, right? But really, it turns out to be quite a lot. And what's interesting is if you look at this curve, then it's not really a straight line. In fact, the first 50 or so years, sea level was going up at a rate of about 1 millimeter per year, a little less than 1. Then it was about 2. And then in the last 20 years, it's more like 3 millimeters per year. So there's likely been an acceleration in the last 100 years of the rate of sea level rise. And although 8 inches doesn't sound like much, to get 8 inches of extra water over 2/3 of the surface of the planet is 16,000 cubic miles of water. So it's really an enormous amount of water that we've added to the oceans, and then it's also expanding because it's getting warmer. So another way that we can measure the oceans rising is actually from space. So we can look at the little critters in the sand and reconstruct sea level change over thousands of years. We have some individual records where we can look at it over 100 years. And over the last 20 years, we can actually measure the rising oceans from space incredibly accurately using a satellite called TOPEX originally, and now the JASON series of satellites. And this is actually the satellite that I work on. So when I go to work every day, I look at the JASON data and make sure it doesn't look crazy and that we're not all about to get sunk underwater. So bring your scuba gear. So this is what the record of sea level looks like in the last 20 years. And it's really amazing because you can actually see seasonal cycles. So every year, the oceans grow a little bit, about a centimeter or so, and then they shrink a little bit, and they grow and they shrink. And a lot of this is actually because water is being evaporated out of the ocean, and it rains down on the land, and it takes some time to run back in. So there's this transfer of water from oceans to land just because of the rain and the water cycle, what we call the water cycle. But every couple of years, there's some big thing in the oceans, like, see if I can do this. In 97, 98, we had a big El Nino, and sea level went up really fast. And then in 2010 and 2011, there was a big La Nina, and actually sea levels fell for a couple of years. And that was because, again, water was being sucked up out of the ocean, and it rained down over places like Australia. They had really bad floods in Australia that year. And it took a while for that water to make it back into the oceans. But eventually it did. And you can see that there's all these little bumps and wiggles, all these kind of interesting things. But what's the one biggest thing you see about this record? It's the 6-centimeter rise over 20 years. So we can measure this incredibly accurately. We can see all these little bumps and wiggles, but really the biggest, most important thing in this record is the 6 centimeters of sea level rise we've seen in the last 20 years. And that's a direct result of global climate change caused by people. So in a lot of ways, this record is really the best indicator we have of how fast the global climate is changing. Because the oceans do two things. They absorb 90% of the heat from global warming, and that causes them to expand and get bigger, so that's part of sea level rise. And then the rest of sea level rise is the melting glaciers and ice sheets. That water runs off back into the oceans, and it literally fills up the oceans and it gets bigger. So this record is kind of the sum of those two different things. So in a lot of ways, it's the most powerful tool we have to measure climate change, to measure human-caused climate change. This is our best yardstick for global warming. But there's plenty of other ways to see that global warming is happening. If we look at the top of the Earth, this was a satellite image taken in 1979 during the summer. Now remember, the ocean at the top of the Earth, the top of the planet, the polar ice cap at the top of the planet is an ocean. The Arctic Ocean fills up with ice. Ice literally just freezes right out of the water and then melts back into it. And in the summertime, that ice shrinks to its smallest extent, and you can really see, you can see it kind of pull back away from the continents. And this is what it looked like in 1979. And this is what it looked like in 2008. And I didn't just cherry pick these 2 years. I can kind of go back and forth between them, I think. Yeah, so this is 79, and this is 2008. I didn't just cherry pick these years. If you look at the area of that ice over time, it's definitely shrinking. So it goes down by almost a factor of 2. It was up close to 8 million square kilometers in the late 70s, and now it's down to close to 4 million square kilometers. And it turns out you can also measure, using other satellites, you can measure how thick the ice is. And the ice is also, it's not just shrunk in area, it's shrunk in thickness. So it's about half as thick as it was 30 years ago. So if it's shrunk in area by a factor of 2, and it's shrunk in height by a factor of 2, how much has the volume shrunk? 4. It's 1/4 the size, 1/4 the volume that it was 20, 30 years ago. So really the volume of ice in the Arctic is shrinking very rapidly, and probably sometime in the next 20 or 30 years, you know, if you draw a straight line here, in another 30 years, the Arctic will be ice-free. So this is something that in the summer, of course in the winter it freezes again and a large area freezes, but in the summertime probably ice-free in 30 or so years, maybe faster. But you can look at satellite images all day and they don't quite convey the same sense of the change. This is a picture of a polar bear, and as you know, the federal government has mandated that any global warming talk contain at least one picture of a polar bear. This is my polar bear, and this is from 2007. And if you go back to the curve really quick, in 2007, that's the minimum extent. Actually, it's not true. I need to update this graph. We've exceeded that minimum again in the last few years. But in 2007, the ice pulled away from North America because of the winds, and there were huge areas of ice-free ocean just north of Canada. And that's where polar bears live. They hunt from the ice. They're really strong swimmers, but the seals are better swimmers. So the polar bears sit on the ice, and when a seal goes by, they jump in the water and kill it and eat it. Now, I'm not a biologist, but probably I think the polar bears will eventually survive this loss of ice because they can always just move south and eat Canadians. But nevertheless, it's one of the first indicators we have that climate is affecting some of the top-level predators. Some of the biggest creatures in the world, at the top of the planet especially, are beginning to feel the effects of global warming and climate change. So this is just sort of a reminder that this is happening. It's beginning to affect species. In fact, species all over the planet are beginning to try and migrate and readjust their climates to survive. So sea ice, remember though, is floating ice. It's ice that's already floating. So when it melts, it does not raise sea level. But if you think about a glass filled with ice water, if the ice melts, then the level of the water doesn't change because the ice was already displacing whatever water it was going to produce when it melted. But if you have ice on land and that melts, the water runs into the oceans and it raises sea level. And in fact, the ice itself can calve off. There's these huge ice streams, these rivers of ice that flow off of the continent into the ocean. If those speed up, then you can actually get faster sea level rise as well. So these are kind of the mechanisms. But we can also measure this loss of ice from space. In fact, the transfer of ice from the land to the oceans, we can see from these two satellites that are called Tom and Jerry, actually are their two names. These are the Grace satellites. Grace is still operating. It's about 10 years old now. And these two satellites chase each other around the planet. And whenever one goes over something heavy, the pull of gravity literally speeds it up, and they separate a little bit. Then when the second one follows, it catches up, and by measuring the distance between the two satellites very, very accurately, you can actually figure out how heavy the thing is that you were flying over. And so in this case, if they were flying over Greenland, you can watch Greenland lose weight. You can watch it lose mass. It's been on Jenny Craig, and it's lost over 2 trillion tons. So she's very effective, Jenny. But literally, you can see every year, Greenland gets some extra ice in the winter because it snows and it freezes. And then in the summer, it melts and runs off, and the glaciers speed up. And this happens every year. But overall, again, we have this huge trend, and in fact, there's some suggestion that this trend is accelerating as well. So this is contributing significantly to sea level rise. It's about 0.5 millimeter per year out of about 3 millimeters today. So it's about 1/6 of global sea level rise is just from Greenland losing mass. And you can see the patterns of it as well. The southeastern tip of Greenland is losing ice the fastest, and that's because the water is warmest there. And in fact, there's some warm water that's starting to creep up around the northwest corner of Greenland, and that's causing ice to be lost from there as well. So we're beginning to see Greenland lose mass from all around the continent, but mostly in the places where the oceans are warm. It turns out that this ice, which runs right off the continent into the ocean, some of it sticks right into the water. And so that means that if the water warms up, it can heat up the ice at the bottom and cause it to speed up and lose mass more quickly. So the ice and the oceans are actually interacting. So it's not just the atmosphere dumping snow or getting warmer or whatever, but really these huge ice sheets in Greenland and Antarctica are beginning to interact with our warming ocean as well. Again, a picture is worth 1,000 words. And if we look around, there's all kinds of really cool photography where you can go back and look where somebody took a picture of a glacier. This one's in Alaska in the 1940s. And then you go back today and you take a similar picture from the same spot, and you can see that the ice has retreated all the way up, miles and miles up this fjord. And it turns out that something like 90 or 95% of glaciers everywhere in the world are in retreat. There are very few that are advancing for different reasons, but really over 90% of our glaciers are retreating and look like this. And Alaska has some of the fastest retreating glaciers in the world. You can go there on a cruise one summer and then drive up in the ship and you see the end of the glacier, and then you go back the next summer and it's 2 or 3 miles farther up. But one of my favorite pieces of evidence that the climate is changing in the last 100 years in a really special way is this picture, this pair of pictures from Antarctica. And if you think about Antarctica, the bottom of the planet, our southern polar ice cap, is a continent. It's a big land mass. And there's this tiny little piece that sticks up towards North America called the Antarctic Peninsula. And this is right at the tip of the Antarctic Peninsula. And it's what's called an ice sheet. And an ice sheet happens when glaciers flow off the land into the ocean, and then they form a big pillow of floating ice. And that floating ice kind of spreads out, and it forms a big ice sheet. Now, the ice sheet is floating, but it's being fed by these glaciers where ice is running off the land into the oceans. And this ice sheet was, in 2002, developed all these dark pools. And this is a satellite image it's called the Larsen B ice shelf. And these dark pools appeared, and then a couple of months later, they flew the satellite back over it, and then almost the entire ice shelf had broken up and collapsed. So all that fuzz is icebergs that have broken off of this big flat shelf into thousands and thousands of little pieces, sort of like foam. And the area of this thing was about the size of Rhode Island, so it was the size of a US state. So it was a really massive ice sheet that just collapsed. And what's interesting to me is that scientists went back and they found out, they drilled a sediment core underneath where the ice had been, and they found out that the ice shelf itself was 10,000 years old. It dated back to the last ice age. So it had survived the medieval warm period and the little ice age and all this climate change, but it wasn't until today's climate change that it finally collapsed. And that means it's the only thing older than Hugh Hefner to break up in the last 100 years. No groan? Okay, anyway. So but it's a reminder that the stuff that's happening today is something that's really unique to our experience of the last 10,000 years of the planet's climate. So I think if you're not looking for global warming, then it's because you're not really looking at the data. Now, that doesn't mean that you can walk out in your backyard with a thermometer and prove that global warming is real, because we still have weather and we still have small changes that are hard to understand that we're still trying to figure out. But if you look in any kind of global sense, at any kind of marker that tells us about the entire planet's climate, you see it really jumps out right away. And things like global sea level rise, the global temperature increase, all these glaciers melting, all this is really evidence that this last 150 years has been special. And the reason it's special is because of the carbon dioxide that we add to the atmosphere. So, what about the deniers? Well, there's still people who claim it's not true. And I think what really eventually gets them in the end is the evidence. If you really just look at the evidence clearly, it's very hard to deny that the planet is changing very rapidly and that human beings are the cause. So eventually I think scientific truth wins, but that doesn't mean that we don't have a lot of work to do. We still have to think about how to deal with this as an entire nation, and in fact it will require global scale changes. So I like to tell people, they always ask what can you do? I like to tell people that really how you vote is as important as driving a Prius or planting a tree. Really, it's not quite enough to just reduce, reuse, recycle, buy some solar panels. Those things are great, and we have to do all those small steps ourselves, but it's going to take some larger action on a global scale to really address this problem, which you can kind of see if you think about what's changing. The entire planet's sea levels are rising. Antarctica is melting. Greenland is melting. These are huge global problems, and they're going to require global solutions. So we have to think big and small at the same time. So a lot of people like to say, well, what happens if you do all these great things? You get us off fossil fuels, we have energy independence, we have cleaner water, sustainable jobs. Well, what if you do all that stuff and then it turns out to be a big hoax and we made the world a better place for nothing? So try to remember, though, that there are a lot of reasons to kind of do these things anyway. We do have to look toward the future and try and find alternative sources of energy and new ways to fuel our planet. And in doing so, we can solve a lot of these other problems as well, with global warming reducing the impacts of global warming as an added benefit. So with that, what I'll do is stop, and you guys can ask me whatever questions you want. I will repeat the questions. Yes, I will. Yes. Thank you. Yes, sir.
So, first of all, thank you. My name's Mike. We thought about these things yourself.
Yeah, so I mean, the question is kind of, are we on the brink of sort of a tipping point where we don't have to add any more CO2 to the atmosphere? The climate starts doing it for us just because it got warm enough to reach a certain level that other things started producing carbon dioxide, these methane hydrates and other little kind of time bombs in the climate system. And that's a super big concern. I think it's really one of the biggest concerns is that some people calculate that we're right at the tipping point. I think we don't really understand those tipping points very well. So, but it's important to have goals and it's important to have a number. And keeping things below 400 parts per million, some people say it should be below 350 parts per million to avoid the worst, most dramatic climate change. So that would mean we would have to undo some of what we've done. We're at 400 and we want to get back to 350, we would have to take carbon dioxide out of the atmosphere and stick it somewhere, preferably underground or someplace it wouldn't come back. You can grow trees. There's some people think about ways to do that, but it's very difficult because as we've added carbon dioxide to the atmosphere, it's also been sucked up by the oceans. So you take a little bit out of the atmosphere, the oceans will give you back a little bit of that carbon dioxide. So you have to really draw down more than just what's in the atmosphere. So it's a big challenge. People think about ways to, people do think about geoengineering and ways to draw down CO2, and it might be that we discover some way to do that. But we can't count on that, and it's certainly easier to put less in the atmosphere than it is to take it back out once it's there. And so I think the way we have to think about it is simply a sort of a cost analysis where you go, well, is it cheaper to build a highway all the way around some tiny little feature, or is it easier to just address the problem head on? And we're kind of building up all of these things to adapt to future climate change rather than just avoid what we could. And I think we have to try and figure out how to avoid as much climate change as we can, but we're definitely going to have to deal with some of it. So it's a sticky problem, and it's one that we have to kind of agree on. And I think it's one that requires a lot of leadership, but it also requires a lot of young people to make a lot of noise and get upset and cause something to change. So you have to keep in mind, that's why I put that slide up about voting. You have to keep in mind that the people who are running the country are representatives of you guys. And if you don't tell them what you want them to do by voting, by calling them up, by writing them letters, by going to see them, then they're going to do whatever they think is best. So you really have to make a case for it. And that's where I think it starts. But I agree that we do have to really, we need to focus on mitigation is kind of the IPCC word, avoiding the worst of the disasters that we can. That means trying to find alternatives to fossil fuels as quickly as possible, and reduce our fossil fuel use at the same time by whatever means we can. And but at the same time, we are going to have to adapt some, and we have to think about things like, how do we get carbon dioxide back out of the atmosphere? What are alternative energy sources? There's a big debate about nuclear power because it too has its problems. Things like the Fukushima power plant disaster, spilling radioactive waste is a huge global issue. But is it worse than global warming? I don't know. It's hard to say. So we have to keep our minds open, I think, for alternative energy sources. And really look at kind of all the options on the table and try and weigh them. So that's my short answer. Any other? Yes?
You think rationing the use of
Right. Right. So is rationing carbon dioxide a feasible policy? I think that's a tough one. The policy questions are really the hardest ones, I think. The questions about whether or not the climate changing has already been answered. But what do we do about it? That's really the heart of the matter. Personally, I think that the simplest, most fundamental thing to me is that we don't pay the cost of the carbon we burn today. And so I think we should pay the cost of the carbon that we put in the atmosphere through perhaps a means like a carbon tax. To me, that's the simplest way, is to tax the thing that we want to reduce, essentially to begin to pay the full cost of the carbon dioxide that we're using, because it has an enormous cost. If you average out over the life of how long it's in the atmosphere for 1,000 years. And the costs that it'll incur because of climate change, because of sea level rise, are going to be enormous. So we should figure out a reasonable way to tax carbon. I think, personally, that's what I think. But we might get to rationing, we might get to other things. There are all kinds of policy tools you could use, but none of them are fun. None of them are fun to vote onto yourself. Yes, just give me coupons and I'll get a smaller car and drive less and live near where I work. But I think that may be an option. But personally, I would prefer that we begin to just pay the cost of the carbon that we use, because I think we do need our economy to help us solve this problem. I think it's a big technological issue, and we need to spend resources on how to solve it. So generating revenue maybe isn't a bad idea. Yes?
So a suggestion would be something like that.
Yes. Should you engage in social movements? Yes, by all means. Twitter about it. Did I say that right? Twitter it, guys. But yeah, absolutely. Social media is a very powerful tool, and to be honest, it's one that you guys understand way better than we do. So if you figure out how to use it and master it, you can become the master of the universe. And you should keep that in mind, because these are really important tools for your generation to change the world. So yes, by all means.
And how does it happen, which is in reference to the planet?
Yeah, that's a great question. I think your question, maybe I could sum it up, is do we need a sustainable economy to solve this problem, as opposed to an economy that's built around growth and increasing its wealth and I would also say the size of the population. A lot of people say that what this all boils down to is that there's too many people on the planet. We have 7 billion now, and we're probably headed for 9 or 10 in the next 20 or 30 or 50 years. It would take like a whole bunch of Earths, the resources of a whole bunch of Earths, to have all of those people have the same standard of living that we have right here in this room. So we have to think about that, because there is a social justice issue as well. I mean, How do we have a planet that only has a small fraction of its population with the highest standard of living, and then huge swaths of it in poverty? If we want to change that, then it takes even more resources, right? So how do we build a sustainable economy that can not have to just grow and swell and eat up everything, all the resources around it? That's a tough question. I don't have the answer. I'm hoping you guys do. But really, I think it's one of the key things we have to figure out. It's one of the really big challenges. It needs asking. That question needs asking, absolutely. In the back, yes. Yeah, I think we're kind of running out of time, but I'll answer that really quickly. No, there's no serious scientists who think global warming is not caused by people.
Well, thank you, Josh.
Thank you, guys.